Hello and welcome. My name is Richard Taverner and I'm your host of Any Further Questions. You are listening to a special episode of Any Further Questions where I sit down with Chris Lintott following each of his 6 lectures to ask him all the questions from our audience that we didn't have time to get to. This time he'll be answering questions from his lecture The Marvels of the Solar System, which he gave on the 25th of October and is now available to watch on our YouTube channel, Gresham College. If you haven't listened to them already, all episodes of this podcast are all available to listen to on Spotify, Apple and Google Podcasts, so please do go and check them out now. Hi Chris, how are you?
I'm all right, thank you.
Good.
Yes, recovering from a whistle-stop tour of the solar system the other day, which was fun. It turns out there was a lot to cover in an hour.
Yeah, thank you for joining me. We'll just get straight down to it. We've got a lot of questions that came in that we didn't have time to get to during our lecture. So the first question I have is, what has been the most startling revelation to your understanding of the solar system following probe observations, and why?
Well, I think it's one of the things that I talked about in the lecture, which was the fountains of Enceladus, this tiny moon of Saturn that's got water springing out of its south pole, and which the Cassini spacecraft fortuitously flew through, giving itself a nice wash after a journey to Saturn, but also detecting the water and going on to analyse it. I think it's important for a few reasons. I think the real headline, although it tells us a lot about Enceladus, which is a place that has an ocean underneath an icy shell and maybe perhaps is the most convincing habitat for life, I think really what it taught us was that the solar system is much weirder than we expected, that even tiny moons, and Enceladus is about the size of the British Isles. Previously, I think people had written it off as a dot, one of 100 or so such objects around Saturn. Even Enceladus is fascinating and worthy of missions and study in its own right. And it's a lesson we learn again and again as we've gone back to explore the solar system, particularly since the 90s. Wherever we go, we find new questions and new places that are worth exploring. You could spend a lifetime studying Titan. Friends of mine are spending a lifetime trying to get a mission back to Uranus, a place we've only visited once. Who doesn't want to go back to Pluto? The number of Mars missions hasn't exhausted the number of questions we've got there. So it's really that one discovery, plus the spectacular images of water flowing into space, teaches us that the solar system is weird and it's worth going everywhere.
We had a couple of questions on Enceladus. We had one from Vince. How does Enceladus Ocean recharge itself if it's been discharging for millions of years, or will it stop eventually?
Yeah, that's a really good question. So there's no way to get more water. So if you think of it as an ice cube melting from the centre, that's the total amount that you've got. And you can work out on the current flow rate that there's enough to keep going for millions and millions of years. And I talked in the lecture about the importance of linking Enceladus to the E-ring, this outer ring of Saturn, which is made up of water expelled from the moon. And so that suggests that this has been going on for a long while, that we haven't been lucky in catching Enceladus just in a short active period. But although it's only the size of the British Isles, that's quite a lot of water. And so, yeah, it's certainly enough for it to be a very, very long-lived ocean. Other places where we talked about water, like Europa, the much larger moon of Jupiter, may have bigger oceans. But there is a claimed observation of something like the fountains of Enceladus from actually Hubble in orbit around the Earth saw what appeared to be water coming from one of the poles of Europa. But it only happened once, and so that might be a more sporadic thing, and the ocean may be calmer. But we really don't know how to tell the long-term story of these worlds yet.
We had a question which wanted you to expand on the water on Europa, just simply saying, and the water on Europa?
Yeah, well, you see, we talked about Enceladus because it's the place we've been to recently. But as I mentioned in the lecture, I'm very excited about missions to Jupiter's moons. In particular, ESA's JUICE mission, which will go to Europa first and then end up at Ganymede, which is another of these icy water worlds, is now 5% of the way there. They've got a brilliant Twitter feed where they have a juice bar that's slowly filling up. So since launch last year, we're 5% of the way there. Earlier this year, since their launch. But yeah, so Europa's an interesting case because the evidence we have for an ocean is all from the surface that seems to have been resurfaced and so on. We think from deposits that we see on the surface, most recently with JWST, that there's evidence that water isn't just pure H2O, that it's salty. and that it may have carbon dioxide mixed up in it as well. So the importance of the carbon dioxide finding is that carbon, of course, is the key to organic chemistry. So it's one of the things we look for if we're looking for a habitat for life. The importance of the saltiness, which comes up in Enceladus too, is that to get salt, you need an ocean that's in contact with a surface. There must be an ocean floor down there. So you could think perhaps of Europa as perhaps a rocky core, something small, and then a water layer, and then the icy outer layers. But what we don't know is how big the core is relative to the water. We don't know how much or how deep the ocean is. We don't know how thick the icy covering is. So those are the questions that this next generation of missions will try and answer. Until we know that, it's very difficult to say much about the nature of the reservoir of water that's there. Is it perhaps just a thin layer? Is most of the moon water? How much of it is in contact with this core? We just don't know at this point, and that's why we're sending these missions. So it's a great question to ask for more information about the water. I think if you come back sort of early 2030s, I'll have a much more detailed answer for you.
As Enceladus passes through the E-ring, is the density of ice crystals sufficient so that the moon can recycle the emitted water for future volcanic eruptions?
Yeah, I really like the idea that everyone's invested in keeping Enceladus going based on these questions. But no, Enceladus is actually slightly off the E-ring. It doesn't pass through the ring itself. So there's no recycling there. What will happen is that ring will get bolder and grander over time. But you'd have to wait a long while for it to catch up with the other rings.
Does what has been found in the solar system over the course of the last decade or so change your view about the chances of life further away?
I think it changes my view about the places that life might exist. So, for example, one of the things that happened when we started discovering exoplanets, planets around stars other than the sun, was that there was some surprise that there were lots of systems that have large planets, maybe Jupiter scale, but certainly lots of places that have planets the size of Uranus or Neptune close to their star. And that breaks the architecture that we're used to in our solar system. You have the Sun, and then you have Mercury, Venus, Earth, Mars, rocky planets, Jupiter, Saturn, Uranus, Neptune, gas giants. And we thought we had a good explanation for why that was so. Now we see all of that mixed up. We see larger planets much closer in. And initially, I think, many people, including myself, would have thought that that's a negative for life. If you're thinking of life on rocky worlds rather than, hydrogen breathing squid in the atmosphere of Jupiter, Sagan's favourite conjecture. But if you're talking about our kind of life, that's a bad thing. We think those big planets have migrated inwards during the history of their solar systems. And so, what's the odds of there still being life on Earth if Jupiter moves from where it is now to where Venus is now? It's pretty low. It's bad news for our planet. But if those planets have a retinue of moons, and they come in with them, or they form in situ there, then you can imagine taking something like a world like Europa, placing it where the Earth is, and you have a very temperate climate. So maybe you have a water world instead of an ice world. So I think the last refuge of every exoplanet scientist writing a paper about discovering these types of worlds, there are lots of ways to make your planet that you found interesting, but one of them is to claim that it might be a place where life could exist, that it exists in what we call the Goldilocks zone, the habitable region around the star, where the temperature's not too hot but also not too cold. If you've got a giant planet in the habitable zone, you just say, well, maybe it has moons. And then you can have a nice artist's impression of the verdant landscape of a water world with the giant Jupiter in the background. And I've played that game myself. We don't yet know whether these planets have moons, but it seems likely all the big planets in our solar system have this large retinue of interesting moons. But I think it also gets at this idea of a habitable zone in itself as well. So, the exact definition of where the habitable zone is controversial, and exactly how you set it up is difficult. It depends on understanding the atmosphere. But it's not too much of a stretch to say if you're thinking about life on a rocky world, on the surface of a body like the Earth, then there's a region around the star where the temperature's right for our kind of life, whatever right turns out to be. Well, Europa and Enceladus and even the oceans of Pluto, if they exist, are all much further out. And so then you have to extend the possibility of life through the solar system and basically admit that almost any planetary system could have homes for life, which is really exciting. Now, what we haven't managed to do yet is change my understanding of whether life does exist. If you've got these habitats, they've got these places where life exists, and maybe the right mixture of chemicals, what I described in the lecture as SNOPs, carbon, hydrogen, oxygen, phosphorus and sulfur, exist. Does life get started? That's the big question. And so far, nothing we've found in the solar system really tells us anything about that. It's why going to Mars, getting samples from Mars, looking at whether life got started on Mars is so important, because if we find that Mars does have life or did have life, even if it was very simple, even if it only happened early on in Mars's history, then that tells us that the cosmic lottery can be won twice in the same solar system. And if that's true, the odds must be low. And therefore we should expect life to have won throughout the galaxy. And we have a galaxy teeming, if not with astronomers, but at least with simple life. If we don't find life, we do a thorough exploration of the solar system, which could take hundreds of years, and we find that despite all of these habitats, there's no life, that Mars is barren, that the oceans of Enceladus have no squid in them, that Europa and Ganymede don't have places where there are bacteria. If the phosphine that I talked about in the surface of Venus can be explained by volcanoes or lightning strikes or something else other than life, then suddenly I think you're back in a world in which life has to be lucky to exist, that the Earth could be the only place in the galaxy where we won this cosmic coincidence. And we can get information on this by studying other planets as well, but it's so much easier to do this when the planets are right there, where we can send spacecraft, where we can go and prod the atmosphere or swim in the ocean, which we're never going to be able to do in the near future for any planet around any other star.
Given the vastness of the solar system and the way that the Earth has life on it, isn't it way more likely than not that there must be life out there somewhere else?
Well, the trouble is, that seems like a very natural thing to say. I've probably said the same thing myself. But the trouble is that makes an assumption about how likely it is for life to get started. You're right that we've rolled many dice in the solar system, but I haven't told you how many sides the dice have. And so you can't assume any odds. We don't know that yet. We do have one little clue, which is that life on Earth got going quickly. We know that there's evidence of life going back well within the first billion years of the Earth's history. So if life was a supremely unlikely event, if it was very unlikely that life would get started, then you might suppose that life would have taken much longer. But there's all sorts of problems with that argument, including the fact that it took 4 billion years to get to intelligent life. And so, the fact that we're here, if intelligent life is difficult to get to once you have life, then the fact that we're here may bias us. It may be natural that we're on a planet where life got started early because we needed the 4 billion years to produce us. But there's at least some weak evidence there. But this is why Mars is important, and getting to Mars and finding life and showing that it independently evolved on Mars is necessary as well. I'm hopeful that if we find Martian life, it will have different DNA, use different amino acids as bases or something like that, and then we don't have to have this argument. But if you find life on Mars and it has the same sequence, same tools, the same building blocks as life on Earth, do we conclude that it's a separate biogenesis, that it's a new form of life, or do we just say, look, there's been transfer between Earth and Mars? That's going to be really difficult to resolve, but it'd be a fun problem to have.
How do you define intelligent life? Because if you're talking about evolution, we are as evolved as, let's say, a slug is. So are we saying intelligent life because we're sort of thinking that we are the pinnacle of intelligence?
Well, I think when we're interested in intelligent life because we want somebody to talk to, it's a sort of narcissistic argument. My usual definition is that intelligent civilizations have both astronomers and gins and tonic. So that's a reasonable working definition, because then you have somebody to talk to, something to talk about, and a drink to have when you sit over it. And Douglas Adams was very clear that all civilizations have their equivalent of gin and tonic. So, but you're right, I think, to point out that the story of evolution on Earth is one in which loads of bacteria and microorganisms are made, and then there's this weird thing going on a larger scale that you can basically ignore. Even if you look at animals, God loves beetles, and yes, there's one intelligent species wandering around as well. So, yeah, you can't assume that evolution is going to progress inevitably to intelligence. Though there's an argument I really like on this by Simon Conway Morris, who's a paleontologist who worked on the Burgess Shale, the first big flowering of complex life in the Cambrian explosion here on Earth. And he has a book called Life's Solution, which argues two things. It says that life in the universe will be very rare. I'm less convinced by his arguments there. But then he looks at the things that evolution is good at doing, and he concludes that once life gets going, you end up with humans, basically humanoid creatures about 6 foot tall with 2 eyes that are intelligent. Basically, it's the Star Trek solution. Like, everyone looks a bit like us, but they've got funny hair sometimes. And I don't know whether that's true, but it's an interesting argument.
Do you think we will find evidence of past life on Mars? If so, do you think it might have seeded life on Earth? You touched upon this.
Yeah.
Your last answer.
I think we're more likely to find evidence of past life than present life on Mars. But I think it's harder to recognise past life. People might remember in the 1990s, there was this announcement in the US. Actually, I think Bill Clinton, as president, made the announcement that NASA scientists had found fossils in a meteorite that had come from Mars. And they found these tiny structures, which one team of scientists had interpreted as looking rather like sort of the kind of fossils you get of bacteria that live in Antarctica. That claim's mostly disbelieved now, or at least there are plenty of other explanations for those structures that don't require them to be fossils. But it gives you a good idea of how odd the evidence is going to be. There's lots of times in the history of studying the Earth where things that we now think of as fossils were interpreted as some other natural process, some non-biological process, whether that's shark's teeth being explained as flints, or even a lot of large fossils being ignored until the 19th century, because unless you've got the idea that there were extinct species, it's very hard to recognise these things. So I suspect you could be on Mars and trip over a fossil of an ancient Martian, and you need to be really, really careful to be able to recognise it for what it is. So I think it's going to be very hard. But now we know the conditions were right for our kind of life. We know where to look. And so I think you can imagine finding things that might be fossils. That's the first step. But probably to do that, we need to get a large amount of the Martian geology back to Earth, because the best laboratories are here rather than on Mars rovers. So I think we're going to need to start doing sample return. There are plans, very expensive plans, to start doing that in the next decade or so. Could Mars have seeded life on Earth? Yes, you can move material from Mars to Earth. So we have Martian meteorites. There's one in the collection at the Natural History Museum down the road. I've held a piece of Mars, which is always a stunning moment. So we know that stuff can transfer, probably via a long period of orbiting the sun. So it's not like you go on an express from Mars to Earth. Could life have survived that? Could life have been transferred? It's not clear, but it's possible. At least it's easier to go from Mars to the Earth than Earth to Mars, though the reverse does happen, we think. And so it's more likely that life on Mars seeded life on Earth than vice versa.
We had 2 questions which talked about water on Mars, so I'll give them both to you and you can kind of give an answer on both. Where is it thought that water formerly on Mars came from or formed? The same or different from water on Earth? And if we think water used to exist on Mars, do we have any theories on where and how it all went?
Sure, good questions both. So the first question hints that actually we should ask the question, where does the water on Earth come from? And maybe that's a question that you've never thought to ask, but it's a profound one. And actually we're not quite sure of the answer. So we think that when the Earth formed, there was a period where it was very hot. And so any volatiles, chemicals like water, will have boiled away. So we will have formed initially a dry Earth, we think. That's what the simulations tell us. And then you have to look around today and you see that we don't live on a dry Earth, particularly the weather we've had in Oxford and London recently. I can confirm it's definitely not a dry planet anymore. And so that water has to come from somewhere. And the best guess is it comes from bombardment from comets or asteroids. So in the early solar system, things are still pretty chaotic. There's a lot of loose material flying around. Lots of it comes from the outer solar system where water ice will have condensed naturally. And so you have this incredible flux of material onto Earth. The exact details aren't clear. We don't yet know what population of objects must have been responsible for water on Earth. When ESA's Rosetta probe went to comet Churyumov-Gerasimenko about a decade ago now, one of the points was to see whether the water there matched, in its isotopic signature, but whether it matched the water on Earth, and it didn't. So that kind of comet, at least, doesn't contribute. But maybe asteroids do. Maybe a few of the cometary families might contribute. And Mars will have had the same. So you will have formed a dry Mars and then been bombarded and gained its volatiles that way.
And are we talking about a deluge of rain, or are we talking about water in asteroids that then hit
Yeah,
Earth?
we're talking about rocket. So if you think of a comet as a dirty snowball, but you can also have icy asteroids. You're thinking about being pelted with rocks and with snowballs.
Hail.
Yeah, but very large hail.
Yeah.
We're talking things on hundreds of meter scales, probably. So yeah, not a shower you'd want to be caught out in. Evidence for this period of heavy bombardment comes when we look at the moon, where lots of the lunar craters, it's thought, formed early in this heavy bombardment. So we know that the inner solar system was a dangerous place to be. So Mars will have gained similarly. It would have had a thick atmosphere of the volatiles that were brought that way. Most of it will have just been stripped off into space. So the lack of a magnetic field and the fact that the planet's small and its gravitational pull isn't as heavy as Earth's will mean that molecules in the top of the atmosphere get stripped off by the solar wind, by high-energy particles coming from the sun. The same process happened here, but Earth's gravity is such that we've hung on to our water. We lost, though, our hydrogen. So there's no hydrogen in the Earth's atmosphere because that will have been lost to space long ago. So most of the water went that way. Some of it, as I said in the lecture, is under the surface. At Mars, we see that there is this ice deposit under the surface, and Mars still has water polar caps that come and go seasonally as well, along with a larger CO2 cap.
We are not the only planet in our solar system. There are other planets, and we had a few questions on those planets. First question, why have Uranus and Neptune been underexplored?
Oh, they're a long way away. It's essentially difficult to get there. I have a long-running argument with Lee Fletcher, who's one of the great experts in the world on the giant planets of the solar system. He's at the University of Leicester. I have an argument with him that I keep telling him that they're boring planets. You look at them in Voyager images. The Voyager 2 probe was the only one that has been to Uranus and Neptune. And, Uranus is a green ball and Neptune's a blue ball with one storm on it. And that's all we've got, really. But they are interesting worlds. They're not like, and I think we've learnt through modelling recently that they're not like Jupiter and Saturn. I think it was easy to think of them as smaller versions of the gas giants, but they have a different composition. Their atmospheres in the cold temperatures behave differently. And so they're more ice giants than gas giants. So they've got perhaps something at their core as well that's made of ice or a more solid core. They have retinues of moons that are fascinating. Triton, in particular, Neptune's largest moon, seems to have ice volcanism, so there are ice geysers and things going on, and maybe another one of these water worlds. It also may have been captured rather than forming alongside Neptune. So there's all sorts of questions to do with those two, but there's a few practical problems. One is that it takes a long time for a mission to get there. That makes it expensive. Because you have to keep the mission team going while you're heading there. The other problem is that out in the outer solar system, you can't really rely on solar power. We've used solar power for missions to Jupiter with the Juno probe, but that's as far as we've gone, which means you need a radioactive source of heat and energy, and there aren't very many of those, and they're called RPGs, but only the US produces them and they're sought after. So that adds complexity to the mission. There is, on both sides of the Atlantic, scientists have identified a trip back to Uranus as a mission that needs to happen, that's a high priority. So I'm hopeful that maybe in the next 20 years we'll get back to Uranus and study it. But there are profound mysteries there, starting with the fact that for some reason Uranus is tilted on its side. So it rolls around its orbit, more or less. And how you get a large planet, which should have formed spinning the same way as the rest of the planets, onto its side, I don't know. It's telling us something about the early solar system. And I think it would be good to go and take a look. you couldn't do both these days. So Voyager 2 managed to slingshot Jupiter, Saturn, Uranus and Neptune, but that was possible because the planets were in a particular alignment. These days you have to choose between Uranus and Neptune, or you wait, I think, about another 70 years, and then they come back into alignment, and then you can go to both again.
It seems that planets get more fascinating the further they are away, the weirder they are. With Venus, how potentially would you go about creating a spacecraft that could survive on Venus for more than an hour?
Oh, well, you need an engineer to ask that question.
Okay.
You certainly shouldn't ask an astronomer. I think the problem is that it's just so hot. It's hot enough that lead would melt. So I don't think it's plausible. I think probably a better approach, if you wanted to sample the surface, would be to have a lot of cheap probes that you could fire and they could survive for an hour each, because that would allow us to explore a large part of the surface. That would be a good idea. And then there are all sorts of fantastical Venus missions. Because of the thick atmosphere, it's a brilliant place for ballooning. And so people over the years, about every 10 years, somebody proposes an airship mission to Venus that would float around in the atmosphere and travel with the planet's winds. And perhaps that could drop probes onto the surface. You get very beautifully 1970s sci-fi when you're thinking about these things. But I think long-term survival on the surface is very difficult.
And is that the same for Mercury?
Mercury's not as bad, weirdly, because the temperature on a planet depends on how close to the sun it is, but it also depends on the atmosphere. In fact, when I was talking earlier about the habitable zone, one of the reasons it's difficult to point at a planet around another star and say that it's in the habitable zone is that it depends what kind of coat it's wearing. It depends what atmosphere it's wearing. If the Earth didn't have an atmosphere, it would be pretty cold out here right now. And Mercury doesn't have an atmosphere, so the surface of Venus is hotter than the surface of Mercury, even though it's closer to the sun. We have probes heading to Mercury. The Bepi-Colombo probe has swung past a couple of times and will go into orbit around Mercury. And I always feel a bit sad for Mercury. I'm not sure I even mentioned it in passing in the lecture. It gets neglected.
That's why I ask. It's not very well talked about that
It's
much.
not. It has its own mysteries. So Mercury's heavier than it should be. So it's got this dense core. On the surface of the planet, there are strange features that seem to suggest the whole thing has shrunk. So I think of it as sort of a jacket potato that's been in the oven too long, which is a very strange analogy. But we don't really know why those things have happened. And one suggestion is that in the chaos of the early solar system, maybe something the size of Mars hit Mercury. And so what we've got is the core of what was once a much larger planet with the outer layers scattered. But we don't know. But Bepi-Colombo will send back great photos of the surface. And it's a fascinating place. But I think it's a planet only geologists can love. You've got no atmosphere, so it's like looking at a hotter version of the moon. And if you're into your volcanic features and your craters, then it's great. But
it's very small, isn't it? So is it the second smallest planet?
It's the smallest, as you know. I've been very clear in both lectures that Pluto's not a planet; it's a dwarf planet. Yeah. I will try and work that in until somebody starts arguing with me about it. But yeah, it's the smallest of the main planets. Okay. But it lives in a region where we have now found many other planets around stars closer to their stars than Mercury is to the sun. So it's clearly not an oddity. It's not a freak. It's normal for planets to be that close.
Is it possible to collect the water Enceladus spews into space and test it?
Yes, well, Cassini's done a little bit of testing as it's flown through, but the next dedicated mission, I think, to Enceladus will fly through and essentially have an onboard chemical laboratory to investigate the water, and perhaps even it would be worth, I think, directly testing for life. Maybe you could see whether anything grows in that water or whether there is an organism there. I'm slightly surprised that hasn't been picked up as the next mission by any of the space agencies. I think it's because people are still working on what chemical lab you'd fly. I mean, ideally, we'd get water from Enceladus, bring it back here and analyse it. We can't do that. That's way too expensive to get back from Saturn. And so I think there's a lot of work to be done on miniaturising exactly the right instruments and flying them. But I would expect us to go back to Enceladus pretty soon.
If you had infinite funding, where would you want to send an ESA spacecraft to explore or search for potential life in the solar system or elsewhere in the galaxy?
Well, infinite funding is very generous, but let's stick to the solar system as this is the topic of the lecture. We'll worry about the galaxy maybe in a future talk. I do think drilling through or melting your way through one of the icy surfaces of the moons. Let's go with Enceladus, I think. You could have an orbiting spacecraft tasting and testing the water, and then if you could take the most advanced chemical lab you could and a camera and melt your way through the surface. We know that the water's not that deep on Enceladus. If it turns out that it's closer to the surface in Europa, we could do that there too. But sending something swimming through the ocean would be it would be an adventure, but it may also make this discovery. I like that there's a story about a proposed mission to Enceladus, and it was a very early concept mission, but so it didn't get picked. It's not yet practical, but it proposed doing exactly this: drilling through the water, sending something with a camera swimming through the ocean. Drilling through the ice and then sending something with a camera swimming through the ocean. And when you do these things, NASA require you to have a set of mission objectives. So mission objective, discover life on Europa. And then you have to list all the possible outcomes and say whether you achieve your objective. So, rocket blows up on launch pad, objective not fulfilled and so on. But these particular scientists had a last one, which was probe eaten. Mission objective fulfilled. So I like the idea that the final thing that you'd get a picture of some teeth. And you discover life, but then not hear from it again. I think that would be fun. And I think you'd then get plenty of funding to go back, if not infinite funding.
Okay. Are the adjustments made by astrophotographers realistic, or do they create false impressions? Yeah,
I made a point of showing a beautiful picture of Jupiter by the amateur astrophotographer Damien Peach, whose work is just incredible. This question comes up a lot in professional astronomy as well, when you're looking at a Hubble picture of Jupiter or something. It's almost two questions. Like, are they realistic? Often they're not, in the sense that if you were hovering outside the Jovian atmosphere, would it look as colourful as we see it in pictures? Probably not. They're often exaggerated. Though I did in the talk show a true colour image of Europa, partly to get across the fact that it's white. It looks like fresh water ice, like a glacier or a snowfield or something like that. So often they're not what you would see. It's certainly true of deep space images as well, but that's another story. But there are a set of guidelines that people follow so that they're not misleading. So, for example, if you create colour images often by combining images taken in different filters at different wavelengths, and lots of the most spectacular images of Jupiter, for example, from Juno, which swoops over the clouds, most of those include information from the infrared, because that allows you to see deeper into the atmosphere. But what you do is you assign the infrared to red, maybe a red filter to green, and then a bluish filter to blue, but you never swap the order. So longer wavelengths will always be red. And so it's a shift in what you can see rather than made up aesthetically to please. Maybe there's nothing wrong with doing that as well. But yeah, these aren't what you'd see if you went on your space tourism trip to the outer planets, though one suspects Saturn would be beautiful in any guise and from any distance.
Is there a reason they need to exaggerate them? What's the reason that they're exaggerated?
Well, these are precious data and we want to see as much as possible. And so the aim often isn't to create a beautiful image. The aim is to see as much detail in the atmosphere of Jupiter, for example, as possible. So by turning up the contrast, perhaps, you might see more features. What's interesting is that all the data is public. And there's a community of people online, mostly around a forum called Unmanned Spaceflight, which people can find if they search for it, where the goal is very different. These are often people with graphic design backgrounds or who are experts in their own right in manipulating images. And they will often take an aesthetic approach to the data. They will say, okay, how can I create a beautiful or an evocative image? How can I tell the story of the spacecraft that are there? So, for example, almost all the images that you've seen from the Mars rovers, particularly from Spirit and Opportunity, two missions that I talked about in the talk, almost all of those come from people on that forum and in that community who have taken the time that the scientists don't have to create a beautiful panorama, to stitch images together, to get the colours right so they feel realistic, rather than using exaggerated colours because we care whether we can distinguish one type of rock from another just by looking at it. And so there is this extra use that the data gets put to that I think has been one of the most heartwarming things of the last 20 years, is that once the spacecraft controllers realize they can make their data open, other people can use them for other purposes. And that's really important.
Are there other animal species that possess biomarkers which allow them to be monitored from space?
Oh, there are lots of these. Yes, I mentioned phosphine in Venus and pointed out that you can monitor penguins from space. It's actually not so much the fact that penguins produce phosphine that makes that easy. It's the fact they do so on an otherwise fairly empty continent. So it's the background. But we do lots of monitoring of all sorts of things from space. I mean, the obvious one is keeping an eye on the health of rainforests, for example, by looking at emissions from rainforests. People look at methane. In fact, there is a project that I think New Zealand are leading, but others are involved in as well, to monitor methane from cattle from space as part of the effort to trace contributions to global warming. And so we can track our own emissions, those of our cattle, but also natural environments. So phosphine is particularly important because it's such a unique biomarker. There aren't many things that on Earth only are produced by life. There's lots of stuff that life mostly produces. One can also do things like look at the global signature of life on Earth. So there's all sorts of projects that I might talk about in a future lecture where people have tried to discover life on Earth. For example, by looking at the spectrum of light reflected off the moon and back. So if you look at a crescent moon, you often see the rest of the moon faintly in what's called Earthshine. Now that's light that's hit the Earth, bounced off the moon and come back to us. So if you image that, you get a very bad spectrum of the Earth, the kind of thing you might get for a distant planet. And so people have tried to look and say, okay, is there life here? And one of the things you see is called the red edge, which is the change in reflectance because of plants absorbing sunlight for photosynthesis. So that's detectable from space. So in theory, we could look for things like that on other planets as well. There's a famous example when the Galileo spacecraft on its way to Jupiter flew past Earth. It was quite a distant flyby. And they did this experiment of saying, okay, if this was a flyby of a different world, could we detect life? And the results from the paper are that they detected life on Earth, but they couldn't confirm whether it was intelligent or not, which, some days I feel the same.
Will the square kilometre array be able to detect biosignatures in radio wavelengths?
Yeah, that's a really good question. So SKA is this marvellous radio project that is covering lots of southern Africa and Western Australia with antennae and dishes that then work together as a massive radio telescope. I actually haven't thought about SKA for looking at particular planets. My guess is that it won't be able to do that. I think the field of view is too large, so I think we won't be able to circle in on a particular planet, but I will check and we can talk about it on a future podcast. What people have talked about with SKA is jumping all the way to SETI, so to doing a proper search for civilizations that are transmitting. And one of the hopes that people are arguing about is that when you think about our emissions into space, there's sort of accidental emissions like broadcasting television in the 50s, 60s, 70s. Those are high-power signals that go out into space. I hope everyone's enjoying the sky at night on nearby stars. There's lots more to come. But one of the strongest emissions is airport radar, because even when you start communicating by fibre optics, you have to broadcast to do radar. If you want to monitor whether anything's going to land at your spaceport or airport, you have to use radar to broadcast. So SKA might well be powerful enough to detect airport radar on maybe the 20 nearest planets. And so that's quite exciting, I think, that the opportunity to do that sort of test. Biosignatures, I think, problematic, but we've got both SKA people and SETI people in Oxford these days, so I'll go and ask.
Why is Pluto not a planet, and who gets to decide?
I think each of us has our own Pluto in our hearts. And so if Pluto's a planet to you, that's fine. Although I've made a point of saying that it isn't. Really, I think, to emphasise that there are lots of these worlds out there. So when Pluto was first found in 1930, the observations that they had to hand made astronomers think that it was the size of the Earth, and so it was uncontroversial that it was a planet. By the mid-90s, we'd begun to find other bodies. We knew that Pluto was much smaller. It's smaller than Mercury. It's smaller than the Moon. And we're finding other bodies that are the same size out there. And so at that point, I think you have a couple of choices. there are probably 200 Pluto-sized things in the outer solar system. Though Pluto is, I think, by a tiny margin, still maybe the largest, but there's another Eris that's almost as big. So you either have 200 planets, or you say, look, there's another category of thing out there, which is a Kuiper belt object, or we call them dwarf planets these days. And we've been here before. When, in the 19th century, people started to discover asteroids, the first few asteroids, Ceres and Vesta, were announced as new planets. The number of planets in the solar system went up. School books must have had to be rewritten. And then once they found that there were not 2 or 3 of these things, but tens and then hundreds of them, we invented a new category. We called them asteroids. And so that's really what happened to Pluto, except that there was this 60-year gap between finding the first one and finding the second one. It was luck, really, that Pluto was discovered. Hard work, but also luck that Pluto was discovered so early. So I don't think it's the same category of thing as the other planets. This doesn't mean it's not interesting. And no one demoted Pluto because it wasn't interesting. It was just this, is it a category or not? Now, does it matter? Maybe. People seem to really care. The body responsible is the International Astronomical Union, which is about 5,000 of my colleagues who had a vote in 2006 and said that there was this slightly convoluted definition of planet that excludes Pluto. But, Pluto will carry on being itself and being fascinating. If people really want to call it a planet in their hearts, then that's fine. One thing I do want to add in our sort of regular series of things Chris wishes he'd known before the lecture was that by coincidence I came across a whole body of work a few days ago that made me think twice about a claim I made in the lecture. I said that the reason Enceladus and Europa and these water worlds are so exciting is that the conditions inside those oceans, on the ocean floor, may be very similar to places on the Earth in the deep ocean where many people think life got started at these hydrothermal vents. And it turns out all of that's true, but I hadn't realised there's a whole camp of chemists who are quite upset about this claim, because if you take the building blocks of life, things like amino acids, and you try to form them in the conditions that exist in the deep ocean, turns out it's too wet. These molecules form through pathways that involve shedding water, and that's disfavoured if you have a lot of water around. So from a chemistry point of view, it makes much more sense to try and form life in puddles, places that dry out, so on land. Why do I care? Well, in an astronomy context, that boosts the Martians. I think Mars is a place where we had exactly these conditions. We had water on land, but drying up and infrequently there, perhaps. And so I think if I'd known that in advance, I may have been a bit more Mars positive. But it just goes to show that we don't understand these questions about the origins of life and why it's so vital to go and see where life exists in the solar system.
Thank you. Those were all the unanswered questions that we had following your lecture and during your lecture. I'm going to end it with a last question about Patrick Moore. Someone wants to ask about what was Patrick Moore like? He calls him a god. Patrick Moore, for those of you that don't know, presented The Sky at Night before his death. And is there anything that you'd like to say about that? How did he influence your career?
Patrick presented The Sky at Night from 1957, from before the space age, all the way through to 2012. And I got to work with him for 10 years, and it was a privilege. Occasionally extremely frustrating, but also a privilege. He was somebody who cared a lot about communicating clearly. I think the thing that Patrick had that he'd earned over time is that when he said to an audience, I'm going to tell you about black holes, the audience went, oh good, I've always wanted to know about black holes. Whereas I think the rest of us, when I say, I'm going to tell, as I will in a future lecture, I'm going to tell you about black holes, I think there's a tendency for people to say, oh, I've always found this stuff difficult. And so I think we can all aspire to that. He was also very good at something I'm trying to bring into the Gresham lectures, at both having cutting-edge things. There were results in my lecture from JWST that I had to rewrite 2 days before the lecture, but Patrick would also start any program about Mars, even if it was showing the latest spacecraft images, by saying, Mars is the 4th planet from the Sun. It's a desert world, and getting across the basics as well. As for me, I date my history as a scientist, really. I'd had a vague interest in astronomy, but Patrick came and talked at my school when I was 11. And he talked about the outer planets. And I have to say, I don't remember anything at all from the lecture except the very ending. Because what he did was he said, well, I've told you what we know about the outer planets, but if I came back in 10 years' time, it would all be completely different because we don't know very much. And it was the first time that anyone had said to me that science was still going on, that it wasn't just a case of learning all the facts in the book and there were new things to discover. So, I finished this Gresham lecture by saying that the solar system was full of marvels, whether or not there's life out there. But maybe I should have said, I told you what we know about the planets. If I come back in 10 years' time, it'll all be completely different because we don't know very much.
For me, it's always very fascinating and more interesting when a Gresham Professor in a Q&A says, we don't know,
yes.
or I don't know the answer to that.
I'm always looking for a chance to say I don't know, or we don't know yet, which is powerful. It's particularly good. There were a few kids in the audience and they're as interested in everything else, but I always like being able to say to them, okay, so you're this age. By the time you're at university, the Dragonfly probe will be at Titan. So we're building a thing now that you can use to study this moon. And I think hopefully some of that will fix. And in 20 years' time, you'll have a Gresham Professor sitting here saying, well, I went to this lecture by Chris Lintott and he told us that we didn't know anything. And now here I am.
Thank you very much for joining me today, Chris, and thank you at home for listening. By the time this episode is released, Chris will be preparing for his third lecture in his series, Oumuamua, our first interstellar visitor. Can you tell us a bit about it?
Sure. So Oumuamua, it's a Hawaiian word. It translates as the scout from really, really far away. And this was a asteroid a body that zipped through the solar system a few years ago. And it's the first time we've identified something that came from another solar system passing through our own. It's controversial. There are people who think it was an alien spacecraft, though I'm not one of them. And it's taught us a lot about the history of our solar system. So I will explain what this is and isn't, why it's controversial, how we're going to find more of these things, and the role they might have played in the whole story of our solar system.
And of course, there'll be a podcast following that lecture, which I hope you at home can join us for. Chris, thank you very much.